Now let's talk about the solution to our problem with heat along a wire. First things first, I've rewritten the implicit equation that I gave you in the intro video. The only change here that you'll see is that I've replaced the coefficient in front of the parentheses with c, the parameter that we created for you in the code. Now if we rearrange this equation a little bit, we can get it in a form that's super convenient for using numpy.matlab.solve. This is because we already know T8 at time 0, and now we know what the coefficients are. So we want to solve for all of the temperatures after time step of h. This shows us then that two of the elements in the matrix coefficients are going to be negative c and 1 plus 2c. The one exception to this is going to occur at the boundaries. I told you these were going to be a little bit tricky, so let's talk about how to deal with them right now. If we take this equation right here, but instead plug in the correct values for t0, we see something interesting. There's a dependence on t negative 1. Now we defined our boundary conditions earlier so that t negative 1 was going to equal t0 for any time. Once we plug this in, we're actually going to get a pretty simple equation, something that only depends on t0 and t1. To help you better visualize how we're going to fill in the array using loops, I've created this diagram right here, which color codes the different possible coefficients that we could have in any slot in the matrix. As you just saw, a bunch of the terms in the matrix are going to be 0, so I filled in big zeros for those portions of the matrix. We know that the temperature of the segment that we're looking at is going to have a coefficient of 1 plus 2c in front of it, corresponding to these blue spirals. We know that both adjacent segments will have coefficients of minus c, which are these pink spirals over here. The two exceptions, of course, occur at the boundaries, where we have one pink spiral and one green spiral, for one coefficient of negative c, and then one coefficient of 1 plus c. Now if I had felt like working really hard, I guess I could have drawn this diagram with 100 rows and 100 columns, making it the actual size of the matrix that we're looking at. But I was feeling lazy, so I scaled it down a bit. However, if we think about it, we know that the number of blue spirals in that imaginary expanded diagram would be equal to 98, because there's going to be one blue spiral in every row, with the exception of the first and last. Similarly, we would see 198 pink spirals, 2 for every row, except only 1 in the top and bottom rows. In the picture I just showed you, the blue spirals corresponded to the coefficient 1 plus 2c, and we said that we would need a loop using 98 iterations to express that. That is exactly what we have here in this top for loop. We can see that the next for loop contains one more iteration, since it starts at an index 1 lower. As expected, this corresponds to the pink spirals in the diagram, where the coefficient equals negative c. Here we have the two exceptions for the two different boundaries, and you'll remember that these were the green spirals in the diagram. We can check and see that we've set the step size equal to 0.5 seconds, as we said that we wanted to. We can run the program and see what we get. Sure enough, we end up with the same solution that I showed you earlier. Since in our initial situation, we had a flame placed under the center of our wire, it makes sense that after some time has passed, we still see a peak in temperature toward the center of the wire, but that the distribution has smoothed out quite a bit. This falls right in line with what we would expect from the heat equation. Right now, the end time is set to 10 seconds, which means that the final graph that we're looking at is the distribution of the temperature at this time. Let's see what happens if we set it to something smaller, showing what's happening earlier on in the temperature change. So here's our distribution after just 4 seconds have passed. You can see that we have a nice smooth curve, a lot like what we saw earlier, except that this time the peak is at a much higher level than it was earlier. When end time was set to 10 seconds, the peak was just under 500 Kelvin. And now we can see that it's resting right above 600. The distribution is also quite a bit narrower, showing that we're further away from an equilibrium position than we were with the larger step